Okay, welcome back. I'm going to start my second example with principle of mathematical induction. Remember, if you have any questions, you can email me at this address here. Okay, let's start. So our problem today, sorry you can't see that, is you have to prove that n cubed plus 6n squared plus 2n is divisible by 3. So it's a little different from the last problem because you can't make the left-hand side equal the right-hand side, but you're still going to follow those 3 steps we talked about in the first video. Alright, so if you recall, the first step is to verify that Pn holds true for any integer that's within the restriction. So our restriction is greater or equal to 1. And we're just going to take n equals 1 because it's the easiest. So we're going to do verify that Pn is true when n equals 1. So P1, your proposition, is 1 cubed plus 6 times 1 squared plus 2 times 1. And this is going to give you 1 plus 6 plus 2, which is 9. And everyone should know that 9 divided by 3 gives you 3, which is exactly what we want, because when it says divisible by 3, yeah, you can divide any number by 3 essentially, but they mean that divide by 3 and it gives you a rational number, an integer rather, a whole number to be exact. So then that's our first step, and we proved it's true. So now we can go into the second step where we assume that pk is divisible by 3 when n is greater, or rather k is greater or equal to 0. Or 1 rather, sorry. And actually I should have wrote is divisible by 3 for this part as well, because Pn cannot be true just when you make n equals 1. That doesn't make sense. It should be is divisible by 3 when n equals 1. Anyways, so pk, remember we're just going to replace n from Pn with k, and that's going to be our pk. And all this is that we're assuming that pk is divisible by 3. Even though we didn't verify for every integer, we're just assuming that. And you just have to accept that. And it comes in handy for our next part, if you remember. So our last part is to prove that pk plus 1 is divisible by 3 when k is greater or equal to 1. Alright, so how do we do this? Well, we just write our proposition, pk plus 1, and then we just replace n here with k plus 1. So let's do that. K plus 1, and then the whole thing is cubed, not just the k. Remember that, be careful for that. K plus 1, this is also all squared, but not the 6. And then plus 2 times k plus 1. Okay, so I think it's pretty clear where we have to go from here. We have to develop this and multiply everything together. And I'm not going to do it all by hand. I actually wrote it on a separate piece of paper, so I'm going to just write out the answer. You guys can take my word for it. If you want, just try it yourself and see if you get the same thing. So when you multiply everything together and add it all together, you're going to get k to the cubed plus 9k squared plus 17k plus 9. So I don't know if you remembered, but in our last example, what we did is that we took pk and we found that pk was actually in our pk plus 1. Okay? So you want to do exactly the same thing here, and almost for every example of mathematical induction, you can find that your pk is actually in your pk plus 1. So that's what you try to do. So in this case, it's actually very easy to see that we can factor out our pk, k cubed plus 6k squared plus 2k out of this. So that's what I'm going to do. I'm going to write it. I'm going to write pk. And then I'm going to see what I have to add to pk to give me back this. So we have k to the third, and we only have 1, no big deal. I took 6k squared, but I need another 3k squared to make it equal. And then here I need another 15k to make it equal here. And I need another 9 to make it equal. So now I have pk here, and because we assume pk is true, it is divisible by 3. We know that this section, which is pk, we already know that this is divisible by 3. So this is no problem. We already know this section of our expression here is divisible. So now we just have to look at this section and somehow prove that this is divisible by 3. Well, if you didn't notice yet, this part of our expression actually has a common factor of 3. So let me rewrite this out. Plus, put these in parentheses so you can see that this is pk. Plus, and we're going to take out the common factor of 3 times k squared plus 5k plus 3. And because we took out the 3, we automatically know that this whole part of this, the section of our expression, is divisible by 3. So now we know our whole expression is divisible by 3, and therefore, by PMI, by the principle of mathematical induction, Pn is divisible by 3 when n is greater or equal to 1. And just make note that when you're trying to prove something, you're not going to say in your conclusion that pk plus 1 is divisible or that pk is divisible, because initially you're trying to prove pn is divisible by 3. So you have to make sure that you go back to your initial expression or statement, whatever, and not your pk plus 1 or your pk. And also you use the n variable here and not the k. Just on a last note, like, you might be realizing a pattern here that every time you do mathematical induction, you try to find pk in your pk plus 1, and as soon as you factor it out, usually the rest comes easy and it just falls in with the rest of it. And in this case, there was a 3 as a common factor, so you could factor that out, and right away you knew that was divisible by 3. And that's usually how it works. So always, always, always try to factor out pk in your pk plus 1. Alright, I hope this helped. Remember, if you have questions, you can email me, and I'll be putting up a few more examples, so check for those. Thanks.